Welcome to this deep dive into core Java. We're going to go way beyond just a checklist of buzzwords today. The real goal here is to connect all those fundamental pieces into an actual architectural mindset, so you can start building systems that are not just functional, but truly robust and scalable.
Okay, so where do we start? Well, let's begin with the stuff that can really get you into trouble. We're talking about the high stakes mistakes. Things like messing up the equals and hashcode contract, using the wrong kind of string comparison, falling for that autoboxing time bomb, creating memory leaks with static fields. Look, getting these wrong isn't just about bombing an interview question. This is the kind of stuff that brings down live applications. So, why do these critical errors happen so often? Well, it's funny, a lot of them trace back to one single fundamental concept. It's right at the heart of the language. How does Java even know if two objects are the same? This is all about object identity. And this slide just perfectly lays out the first trap. On the left, you've got equals, which is reference equality. Think of it as asking, are these two variables pointing to the exact same spot in memory? On the right, you have dot equals, which is logical equality. It asks a much better question. Do these two objects, wherever they are in memory, represent the same value? For comparing what's inside your objects, the choice is clear. It has to be dot equal. Now, this slide here, this gets to what I like to call the sacred Java objects contract. And let me be clear, this is not a friendly suggestion, it's a hard and fast rule. The contract says, if two objects are considered equal by the dot equals method, they absolutely, positively must have the same hash code. This is the bedrock that all of Java's hash-based collections like HashMap are built on. Which leads us to a really critical question. A question that honestly every single Java developer needs to be able to answer on the spot. If you go and override the equals method in your class, but you forget to also override hashcode to match, what actually happens? What's the real consequence? The answer? It's a disaster. This diagram shows you exactly why. When you put an object into a hash map, its hashcode tells the map which bucket to store it in. Simple enough. But when you try to get it back, the map uses the hashcode again to find the right bucket. Then it uses equals to find the object. If you broke the contract, the get method is going to look in the completely wrong bucket. Your object literally disappears. It's still in the map, taking up memory, but you can never get it back. It's one of the most classic and costly bugs you'll find in production. All right, let's zoom out for a second. We've talked about the logic in our code. Now let's look at the engine room where it all actually runs. Because if you don't understand how memory works, you'll never build something that's truly performant and stable. And this illustration is just brilliant. It shows the two core memory areas you have to know about. On the left is the stack. Think of it as a neat, tidy, and private workspace for each thread. It's where your method calls and local variables live. It's super fast. On the right, you have the heap. That's the big, shared warehouse where all of your actual objects are created. So if we boil it down, the key difference is this. Stack memory is for your primitives and references, and because every thread gets its own, it's automatically thread safe. It just works. The heap, on the other hand, stores the objects themselves. It's shared by all the threads, and that's where you really need to be careful about things like concurrency and memory management. Now, people love that Java has automatic garbage collection, and it's great. It cleans up objects that you're not using anymore. But, and believe me, this is a very big but, it is not magic. It cannot fix a logical memory leak. If you have a static field holding on to some huge object, as you see here, you've basically told a garbage collector, hey, you can never, ever touch this. That object will never be unreachable. And that's how you create a slow memory leak that can eventually crash your entire application. And here's another one of those interview killers from the beginning, the autoboxing time bomb. See, Java is helpful. It automatically converts a primitive int to an integer object and back. The problem is, an integer object can be null, but a primitive int cannot. So what happens when you try to assign a null integer to a primitive int? Boom, an immediate null point exception. It's such a simple mistake, but the consequence is a hard crash. You know, understanding performance isn't just about speed. It's about predicting the future. It's about knowing how your code is going to behave when it's under serious pressure. And this chart for big O notation says it all. See that flat line for O1? That's the dream. Your cost stays the same no matter how much data you throw at it. The ON line, scaling linearly, that's usually okay. But that ON squared line that's shooting for the moon, that is a scalability killer. That's what grinds your entire system to a halt when you get a sudden spike in traffic. Okay, now that we have a feel for the machine underneath, we can zoom back into the code itself. Let's talk about the blueprints. How do you write code that is maintainable and flexible enough to adapt when things change? And right at the heart of any flexible design is polymorphism. It's a big word for a simple idea, being able to treat different objects in a uniform way. It is the engine that drives frameworks like Spring. And a huge architectural decision you'll make is whether to use an interface or an abstract class. The rule of thumb you see here is perfect. An interface defines the what. It's a contract of capabilities. An abstract class can provide some of the how. It gives you a head start with some shared behavior.
So let's apply that thinking to a really common choice. Which list should I use? This flowchart is pretty much your complete guide. Do you need to grab elements by their index, like get of 5? Use an array list. Honestly, that's the right choice probably 90% of the time. The only time you should even consider a linked list is if you're constantly inserting and deleting items from the middle of a very large list. And for maps, the choice is usually just as straightforward. This table nails it. If you need pure, raw speed and you could not care less about the order of the items, it's HashMap. Every time. If you absolutely need your data to stay sorted by the key, maybe you're generating a report or a leaderboard, then you use a tree map and you just accept that it's a little bit slower.
Finally, let's touch on concurrency. People get volatile and synchronized mixed up all the time, but these images make it crystal clear. Think of volatile as a traffic light. It guarantees visibility. It ensures that when one thread changes a value, all the other threads see that new value immediately. Now think of synchronized as a bank vault. It guarantees atomicity. It locks the door and ensures only one thread can be in that section of code at a time to complete its operation. They solve two completely different problems.
So how does it all come together? All these individual pieces, object identity, memory, data structures, concurrency, how do we connect them? This is the moment where we stop just being a coder and start thinking like an architect. This diagram really shows that final leap. At the very core, you have polymorphism, which lets you build loosely coupled systems. Then you supercharge that with annotations, which add all this rich metadata and configuration. And then you bring in reflection, which lets the system dynamically change its own behavior while it's running. These three pillars aren't just abstract ideas. They are the literal building blocks of powerful frameworks like Spring and JPA. You're not just learning syntax, you're learning the language of system design. And really, what this all comes down to is that every single choice matters. Architecture isn't some grand document you create once. It is the sum of thousands of small decisions you make every single day, from choosing equals dot equals over double equals, to picking an array list, to knowing when a variable has to be volatile. So don't just write code that runs. Write code that endures. Code with intent.